I think I want to work on logs. 'Cause
Got some problems?
not on me. But we're starting into them, and you said that this session you wanted to go over logs with me.
All right. Every discussion with logs begins right here. For example, 8 equals 2 cubed. This equation over here is an exponential expression. It is not an algebraic expression, and you can't solve it algebraically.
Mm-hmm.
So you need to know how to convert between exponential and algebraic. So what's the logarithm, between exponential and logarithmic? So what's the logarithmic expression of y equal b to the x?
Log b, y equals x.
Yeah, the only thing you really have to remember is that logs are exponents.
Mm-hmm.
In other words, if logs are exponents, then that has to be true. And
Mm-hmm.
you always know where the b goes. The b goes down there, and the only other place for the y could be there. So what's the logarithmic expression of 8 equals 2 to the third?
It would be log 2, 8 equals 3.
All right. Is that the way your teacher expresses that? She says log 2, 8.
Log, well,
What I usually
she hasn't
say,
really expressed it as more just kind of wrote it down and saying as 2 to the cube, 2 cubed is 8.
well,
It's more,
that's the exponential expression.
yeah,
Is 2
okay.
cubed is 8. But if I'm talking about this with somebody, I'm going to say log base 2 of 8 equals 3. And I'm
Okay.
going to call the 8 the argument. In other words, the 8's the argument, the 2 is the base, and the 3 doesn't need any description. All right. So as long as you can go back and forth between these two, that's a good first step. Now, there's a few very common rules of logs. The 3 primary ones. Let's even number them. What's the log of a times b equal to?
Um, I don't know.
The log of a plus the log of b. In other words, it's the same rules as you have with exponents. When you are multiplying inside the
Adding.
argument, then you add the exponents, right? Well, that's an exponent, that's an exponent. So multiplication produces addition. Division. Log of a divided by b equals what?
Log A minus log B.
And thirdly, and this one's probably the most important one, the log of a raised to the b power equals what?
Log A times log B.
No? Is it allows you to do is to take that exponent and put it on the algebra line. In other words, that becomes this.
Okay.
Okay? And all three of these rules are only true, of course, if the bases are the same. In other words, I could have log base 3, and as long as I have log base 3 over here and here, then I'm fine. But I can't have log base 3 here and have one of these be log base 5.
Mm-hmm.
Okay. So let me give you a problem on this first rule. what is the log of 6 going to be equal to?
Um,
And in fact, let's make it base 3. What's the log base 3 of 6? Using rule number 1.
um, log of 3 plus log 3.
You're close. Log of 3 plus log of 2. See why?
Oh, okay.
In other words, 2 times 3 is 6. So I could have written this thing as log of 2 times 3.
Okay.
Okay, and then that's where you can separate it out. Now, another interesting property of logs, let me write these secondarily, because you have to know them, and that's the log base b of b is always equal to 1. So this log base 3 of 3, I can replace with a 1.
Oh.
So the log base 3 of 6 is actually equal to 1 plus the log base 3 of 2. And of course, you'd have to get that out of a calculator. What kind of calculator do you use, Cole?
TI Inspire.
Okay. So you have more, in other words, you're not restricted to just natural log and log base 10, common log.
Yeah.
On the Inspire, you can put in whatever base you want. In other words, if you want to know what number that is, you can put it into your calculator, log base 3 of 2. Most people would need to use the change of base formula. And the change of base formula says that the log base b of a equals the log of a divided by the log of b. And if you had a calculator that only had 2 log keys on it, common log and natural log, you would always need the change of base formula, because that's the only way you could get an answer for that. Log base 3 of 2. In other words, that's going to be the log of 2 divided by the log of 3. And believe it or not, that can be any base. Also happens to be the natural log of a divided by the natural log of b. Also happens to be the log base 17 of a divided by the log base 17 of b. In other words, all 3 of these ratios are the same, which is interesting thing to know, is that once you use the change of base formula, you can be in common log, you can be in natural log, you can be log of whatever base you want. Each of these ratios are the same number, regardless of what A and B are. All right. So, expand that. You're going to have to do 2 things with logs, at least 2. And that is, you're going to have to be able to expand expressions based on those 3 formulas I just gave you. And you're going to have to be able to condense. And they will ask you an equal number. So you have to be just as proficient at condensing as you do expanding. Well, let's expand first.
So would that be log x plus log y minus log z?
This actually proves very helpful in calculus.
Hmm.
In calculus, it's extremely difficult to find an integral of products and quotients. And that's what we have here. So we have two products in the numerator, and then the whole thing's being divided by z. So if we can separate it into things that are being added and subtracted instead, now it's really easy to do these three. The integral of the sum is the sum of the integrals. And each one of those integrals is easy to do. It's just this one that's tough to do. So being able to separate it into things being added and subtracted is pretty big. About that one.
So just log x squared minus log z cubed.
Okay, that's step one. That's not fully expanded. In other words, you have to do the third step also.
So
Just to bring the exponent down in front.
okay, so 2 log x minus 3 log z.
You got it. Now, let me get my book just so I can get a series of problems that I can give you. Solve this problem. Can you solve for x? No, x is between 2 and 3, right?
Mm-hmm.
But figuring out exactly what it is, there's no way to do that algebraically. In fact, there's no way for you to do it on your calculator.
Put it into a log.
Exactly. In other words, anytime you're faced with an exponential equation where your variable is in the exponent, always the way to solve it is to take the log of both sides. And you can use any log you want. I'm going to use natural log. Okay, so that's step one. Now step two is to take that exponent and bring it down on the algebra line. So we have natural log of 7 equals x times natural log of 2. And finally, now we can solve this thing algebraically. It's now an algebraic expression. And x is natural log of 7 divided by natural log of 2. And one thing that's always really important to remember is that logs are just numbers.
Mm-hmm.
A lot of people get real confused because they tend to think of logs as variables or some strange thing that they don't understand. That is a number. Natural log of 7, you can get out of your calculator, divide it by the natural log of 2 out of your calculator, and you'll come up with the answer, which I believe is approximately 2.8. The exact answer is this. In other words, if this is one of those things where they say give your answers an exact expression, this is the only exact expression. Any decimal you come up with is going to be rounded off. Maybe it's 2.81, maybe it's 2.813, whatever. It's an irrational number that goes on and on forever, just like pi. That's why you don't use decimals for pi, you use pi. Same thing for logs. Let me have a look and see if I can find some problems where you have to condense. It's odd to me that this chapter in my book starts out with compounding interest. And the reason that's odd is that you can't solve any of those problems if you haven't had logs. In other words, last week we were trying to solve this problem. There's your general formula for, you've had continuous growth, haven't you?
Mm-hmm.
Okay, so that's the formula for continuous compounding. So, if somebody said you started with $100 and you want to know how long it's going to take to turn that $100 into $1,000, if you're earning 8% a year, that's what you know. You're going to start a bank account when you're a young man with $100, going to earn 8% a year in some universe, not ours, but in some universe. And how long? In other words, we have to solve for t, so we're solving for that exponent. Now, this is what I find puzzling in the book, is they give you these kind of problems, but you can't solve for t until you've had logs. And once you've had logs, now you can solve for t. How would I solve for t here?
Log both sides.
Not yet. You don't log both sides until you get it isolated as much as you possibly can.
Oh, divide by 100.
Yeah, notice that 100 is not being affected by the 0.08t. It's just a multiplier. So I'm going to first of all divide by 100. And now I have to solve this problem. How do I do it?
Turn it into a log.
Well,
Log
you
both
don't
sides.
really turn it into a log. That's not the proper way of thinking about it. Proper way of thinking about it is you're going to take the log of both sides.
Okay.
Just like in any algebraic equation, you can do whatever you want to the left as long as you do it to the right. And I mean whatever. You can square it, square root it, fifth root it. You can take a derivative, you can take an integral. You can do any mathematical process you want as long as you do it to both sides. Well,
Hey, stop it.
in this case, taking the natural log of both sides works beautifully, because remember that one property where I said the log base b of b is always 1. That's because b to the 1 power is equal to b. Okay?
Mm-hmm.
Notice what this equation is going to turn into. I'm now going to have natural log of 10 equals 0.08t, that exponent, which I'm now bringing down in front, times natural log of e. Well, what's the natural log of e equal to?
Natural log of 10. I don't.
If
I,
it's true, when I say natural log, what's the base? The natural log means base e. In other words, this is the same thing as this. Okay.
Okay.
So when I say natural log of e, I'm fitting that
Log.
formula. That's 1. So I can erase
Okay.
that, replace it with a 1, which I don't need to write, and now I can solve for t. T is going to be natural log of 10 divided by 0.08. And that'll tell me exactly how many years it takes to increase your money by a factor of 10 if you're earning 8% per year. Let's talk about graphs of logs. Much like exponentials, you can't really tell what base that is by just looking at that curve. That could be log base 10, that could be natural log, that could be log base 1017. And the reason is that they all go through this same point. Now some might have different shapes. One of those logs might look like this, and one of those logs might look like this, but all three of them go through that point, and all three of them are asymptotic with the y-axis, which is x equals 0. So when I just draw one, you can't really tell what base that is. So know that. In other words, it's a lot like exponential curves. Remember exponential curves all look like that? You can't really tell whether that's 2 to the x or e to the x or 10 to the x. However, it goes through this same point, 0, 1 instead of 1, 0. Now, notice something here. This is, we'll call that y equals natural log of x. This curve is y equals e to the x. They are reflections of one another about this line right there, y equal x, which makes them what?
Inverse.
Yeah, this is the perfect inverse of that. Now, do not confuse inverse with equivalent. This is not the same expression as that. Here's what the same expression would be. If I had y equal e to the x, well, the logarithmic expression of this is natural log base e of y equals x. Well, notice that that is not the same as this thing in the upper right that I've circled. Not the same at all. On the left, these two are exactly the same. On the right, this one's the inverse of this one. When I first studied logs, that was always very confusing to me, especially when I tried to learn it 30 years later. Distinguish between equivalencies and inverses. The fact that logs are also the inverses of exponential expressions or equations is very useful and very helpful and very important, but it's not the same. And you won't really deal with this aspect of logs right away at all. I just wanted to point it out so you wouldn't get confused by it. Always know that you have to be able to go back and forth between these two on the left. You have to be able to take an exponential expression or equation and convert it to its logarithmic form, and you have to be able to take a logarithmic equation and convert it to its exponential form. For example, I said natural log of y equals x, let's make it natural log of 3. How do you solve that? And hold on, let me change that a little bit. Let me change it a little bit. I want to make this a little more descriptive. If I said log, common log of 2 equals x, how do you solve that?
I have no clue.
Turn it into an exponential. In other words, this is 10 base because it's common log. So how would I solve this? Turn it into an exponential, which would be what?
10 to the x equals 2.
Yeah, I didn't mean 2, I meant 100. If you're solving that, common log of 100 equals what? Well, then you'd say 10 to the x equals 100. Well, now x is clearly 2.
Mm-hmm.
In other words, I can solve it once I turn it into exponential. And that's true with a lot of your initial problems that you'll get. You can, when you have a log equation, the solution frequently lies in turning it into exponential expression. And when you have an exponential expression, the solution always lies by turning it into a log expression. So going back and forth between exponential and logs are the most common thing you will do in terms of solving log problems. Time for one more, maybe 2 more. Expand that expression as much as you can.
Okay, so you have log base 4 of 4 minus log base 4 of 3.
What's that equal to? Remember, if your argument is
4 to the x equals 4.
it's 1.
1. Oh, okay, yeah, okay.
In other words, if I said what is log base 4, I'll let it equal x, solve for x. Well, now you know that to the x power has to equal that. So it's always 1. As long as this number is the same as that number, it's 1. So I can now convert that to the number 1. Now this, I don't have to, I can't really do anything with it. I could say it's the log of 3 divided by the log of 4 using the change of base formula. And you can certainly get that number off of most calculators, the TI-84 or 83. You wouldn't be able to get this number off of, you wouldn't be able to get that number off of a TI-84. You will off your Inspire without using the change of base formula. But it's good to know that change of base formula despite the fact that your Inspire can do it. All right. Cole, next time try to bring me some problems because logs can be simple, logs can be tough. I never know what degree of difficulty they're doing with yours. So I never really know, how far to take you with logs.
Okay.
It just works a lot better if you give me the problems because I know that's what you're covering in class.
Yeah.
All right. Talk to you
All right.
next Monday.
Talk to you next Monday. Bye-bye.